Yeah, so this talk is partially joint work with Greg on some of our work together on collection frames, and partially some of my own work coming out of that. And so proceed. The plan for the talk is to give a little bit of background and motivation for collection frames, which is something that Greg and I have been working on for the past year or so. And then I'm going to spend the rest of the talk talking about some interesting features of collection frames, a couple of different classes of them, and some features, some ways in which they differ from other approaches to frame theory for relevant logics and relations to other approaches. So have the background, and then the first sort of point of interest is the role of reflexivity in the definition of validity and how that plays out in collection frames. So I'll talk about that for a bit, and then I will talk about functionality and relate collection frames that obey a kind of functionality constraint to Alistair Urquhart's Semilattice frames for relevant logics coming out of his dissertation. And then I will sum up with a couple of general morals from the talk and move over to discussion. Cool. All right, so let's start with collection frames. So before we get to collection frames, we'll just start with very simple frames for logics. So Kripke frames for classical modal logics, right? Those are very nice, very simple. We have a non-empty set of worlds W and a binary relation on W. That binary relation R doesn't need any conditions. You can impose them if you want, but generally don't need any conditions. And you can use these frames to interpret a wide range of modal connectives. And these are, of course, very well studied. And they have lots of pros and a couple of cons I'll just highlight for thinking about. So they offer a very flexible framework for studying a wide range of notions. They provide a really illuminating analysis of modality. They're fiddly, but just like the right amount of fiddly. Like you can sort of get into it and it's not overwhelming how much stuff you have to check. So it's really, they're fun to tinker with and easy enough to tinker with that it is very satisfying, right? And one of the other nice features about it is binary relations are just everywhere. Like you look around and it's like, oh, there's one over there. They're just, you can't get away from them. They're all over the place. So you can model all sorts of things using these Kripke frames with binary relations. They do have a couple of cons. First off, binary relations are kind of limiting. With only 2 slots, there's only so much you can do. There's some things that you're just not going to be able to model using them. Even some kinds of like modal notions, some kinds of necessity, you're just not going to be able to model using binary relations. And one other con that's sort of maybe a little bit less apparent is that if you stick 2 binary relations together, the result is a binary relation, right? It's not, you don't get more options, more slots by doing that. You get 2 slots. You just keep on sticking them together and you keep on needing 2 slots, which is sort of related to the limiting aspect of being binary. Okay, so let's move to ternary relational frames. Let's just add one more slot. So ternary relational frames, also called Ratley-Meyer frames, right, have been used to study relevant logics and substructural logics and provide a really nice frame theory for them. And we're going to talk only about positive logics for today. So there's usually another bit to the ternary relational frames, the star used to interpret negation, that's not going to appear. So what we have, right, we have a non-empty set of worlds or points P, a non-empty subset of those, the normal points N. We have a heredity ordering on points, and we have a ternary relation. And right, that's what the left-hand column is saying. Then we have a few conditions on those that we need to get things off the ground, right? We need the heredity ordering to be a partial order or pre-order. There needs to be some interactions between the heredity ordering and the ternary relation. There needs to be some interaction or relation between the heredity ordering and the normal points in the relation and the heredity ordering and the set of normal points. You get everything sort of working appropriately. So I have a lot of conditions, and these things have lots of pros and a couple of cons, right? So the pros, again, this is a very flexible framework for studying substructural and relevant logics, has lots of connections to other areas of logic, a lot of interesting connections to algebra, combinatorial logic. It is formally and philosophically very rich. There's a lot of material to work with there. Robert Meyer, one of the creators of the framework, called it the key to the universe in light of its connections to logic, algebra, and combinators. And one of the pleasant features of it is if you have a ternary relation, if you have two ternary relations and you compose them, you stick them together, you can reach new relations of absolutely amazing arities. They just keep growing, which is kind of useful and is in some ways where the idea for collection frames takes off. So they have some cons, unfortunately. So they are fiddly. They can be there's a lot to check, especially when you're using ternary relational frames for stronger logics, because those have some frame conditions that are a little bit, say, fussy. There are existential conditions that are a bit of a pain, can be a bit of a pain to check, and ternary relations are a bit less common than binary relations. Of course, there's some very pleasant and familiar ternary relations out there that you just run across, like especially in geometry, right? You have betweenness or collinearity, like excellent ternary relations, but they are a bit less common than say the binary relations you see with Kripke frames. So here are what do some of the conditions look like? Well, we're going to just focus on stronger logic. So like RW and R, the positive fragment. So that's the reason for the plus, right? So for these logics, we have the frames that I had from a couple slides ago. And we're going to use these definitions. They're pretty common. Two different ways to compose relations. Right? You can stick them together in these two ways. And of course, you can just iterate these and get all sorts of compositions. But we have these, and then we have some frame conditions. So first frame condition is that you can permute the first 2 points. That's fine. And then the second condition says that the association in the first 3 points doesn't matter. You can move it back and forth. And then we have this third condition, which is a kind of contraction condition for R. And of course, if we drop that condition and just have these first two, we get frames for RW. Right, now, if you look at those, you can see that order of the everything but the final point doesn't matter in light of this first condition. You can move them around. And then association, the bracketing for everything but the final point doesn't matter because you can just scoot the brackets back and forth. And then combine that with permutation, and you can reasonably just drop the bracketing and not really pay attention to the order of stuff, the order of the points up till the final one. And under that description, right, the points up to the final one seem like they're behaving kind of like a multiset. And so a multiset is kind of like a set. It's not going to pay attention to the order of its members, but it's different than a set in that it is going to pay attention to how many times an element is a member of it. So in a multiset, right, this multiset AAB is distinct from the multiset AB because A occurs twice over here on the left and only once over here on the right. But the multiset ABBC is the same multiset as this one over here, BACB, because they have the same members occurring the same number of times. Right? And so that is sort of one of the motivating ideas for collection frames. What if we take, instead of dealing with a ternary relation and imposing a lot of conditions, try to get imposing a lot of conditions, what if we just take collections of points and work with those? And so that's what we've been working with, this idea that rather than a ternary relation on points, we're going to use a binary relation where one side of the relation, the left side, is takes finite collections of points and then relates those to single points. Right? And collections here, sort of the generic term we're using, is they can be any structure. You can have trees, you can have lists, you can have multisets, you can have sets. For today, I'm just going to talk about multisets and sets, for the most part, just multisets. And so what do these frames look like? Well, they're going to be pairs PR, where P is a non-empty set, and R is a compositional relation on that set, relating collections to points. And so what does compositional mean? It means this. All right, so from multiset, we're going to take the set of finite multisets over a set of points and say it's compositional. This relation is compositional if and only if, for all finite multisets x and y, and for all points y, we have these two conditions. These are two halves of a biconditional, and they play different roles in the theory, and so I find it useful to sort of separate them out. So this one direction called transitivity. So if a finite multiset x relates to little x, and x combined with y relates to little y, then x combined with y also relates to little y. So call it transitivity, even though this condition is not literally transitivity, it is sort of reminiscent of it in the same way that cut is reminiscent of transitivity. Okay. Then the second condition, evaluation, is the converse of that. All right, if x combined with y relates to little y, then there is a point, you can sort of evaluate x to some point, and then use that combined with y to relate to y. So rather than having to use the whole multiset x, you can just condense it down to, you can find some point it condenses down to, and just use that combined with y. And those are the fundamental features, requirements on a relation, multiset relation. And then we have this other condition, reflexivity. A multiset relation is reflexive, just in case for all points, the singleton of that point relates to that point. Right? And so that is the multiset version of compositionality. And so you can get relations, collection relations on other collections defined similarly, replacing the multiset stuff with set stuff or list stuff. So like to define reflexivity for set relations or set frames, we just replace the multiset brackets here with the set brackets, and instead of using, say, multiset union here, we use set union with this being a set and this being a set. All right, so in pictures, hope these are helpful. So on the left, we have transitivity with the solid line being the relations in the antecedent of the condition, and the dotted line being the relation, the consequent. So if x, big X, multiset big X, relates to little x, and you can combine little x with y to relate to little y, well then you could just take big X together with big Y, and that itself relates to little y. Generally, for evaluation, if x together with y relates to little y, you could instead find some point x, little x, that the multiset x relates to, and combine that with y, and have the result relate to little y. So those pictures are, I hope, helpful in thinking about how these conditions are working. Okay, so one of the features of collection frames, particularly multi-set frames and set frames, is that they're comparatively easy to find examples of. So two compositional reflexive multi-set frames on omega are the following. So we have the product frame. So we have x relates to y, just in case y is the product of all the members of x, with the empty multiset relating to 1. And some products. X relates to y, just in case y is the product of some members of x. with empty set relating, or empty multiset relating to 1. And it is sort of pleasantly easy to find examples of these sorts of frames. So the first frame, the product one, is a functional, the relation there is functional in the sense that I'll talk about more later. The second one is not. So it's, it's going to be comparatively easy to find functional relations and also non-functional, and potentially non-functional relations. And so at this point, I think I'll also mention all the relations I'm going to talk about today are compositional. So I will often just drop compositional from when I'm talking about the frames, but you should understand all of them as being the relations as being compositional in the sense I mentioned. All right, so I've given you some frames. Now we can define some models on these. So a verification relation on them has to obey one condition, and that's a heredity condition here, which may be familiar if you're familiar with ternary relational models for relevant logics. All right, so if P is verified at point X and singleton X relates to Y, then P is verified at Y. So verification is preserved up these singleton relations. So the singleton relations here are doing a lot of the same job that the heredity relation in the ternary relational frames is doing. Okay, so we can, given a hereditary verification relation, we can extend it to the whole language like this. Conjunction and disjunction work like in the familiar ways. Conjunction is verified just in case both conjuncts are. The conditional implication is verified at a point just in case for every y and z. If the multiset xy relates to z and the antecedent holds at y, then the consequent holds at z. And fusion, right? A fuse B is verified at x just in case for some y and z. If the multiset yz relates to x, or sorry, multiset yz relates to x, and both A holds at y and B holds at z. And then we have the Ackermann constant, which is not going to feature too much in this talk, a bit later. So the Ackermann constant, little t, is verified just in case the empty multiset relates to that point. And bottom, which will not feature in the talk really, we can throw it in there if we want. It's not going to feature in. So that is how verification is going to work. So we have models, and at this point, it would be very natural to define validity. I'm going to delay that just a little bit to talk about proof systems, get those on the table, and then talk about validity. So we can give a sequent proof system for many logics along the lines of what you find in, say, Restall's Introduction to Substructural Logics, or Slaney's General Logic paper. So we have sequence where using structures, and so structures are defined as follows. You can have formulas or structures. We have this special empty structure epsilon to mark logical truths. Then we have an intentional structure combination. So if gamma and delta are structures, then you can combine them with a semicolon. And then we have an extensional structure combination, comma. Okay, so then sequence on the left-hand side are going to have a structure, and on the right-hand side are going to have a formula. And I'm not going to give you the whole proof system, but I'll give you a little bits of it, glimpses. If you would like to see more, there's a paper with all of the details. Let's see here. So basic features of it, we have an identity axiom, right? A implies A. And then we have a cut rule, which says that if gamma implies A and gamma prime has an occurrence of A somewhere in there, and that implies B, then the structure you get by replacing the occurrence of A with gamma, and gamma prime also implies B. And then we have different structural rules for the different modes of combination. So comma has the extensional structural rules. There are others. So we have a contraction rule, a weakening rule, and some others. And then we have rules for combination, for the intentional combination. And so here we're focusing on RW. So we have permutation, and we have this association rule. We don't have contraction because we're working with RW. We have, here are the epsilon rules. We can, whenever we have a structure, we can pop an epsilon on the left with intentional combination. And if we have an epsilon on the left, we can pop it off. And that all works nicely. And then, okay, we have rules relating for little t, and little t is connected to epsilon, right? We can trade an epsilon in for little t, and then we have this axiom for little t. Then we have some other connective rules. These are going to be the more or less standard rules. The conditional and fusion are both connected to the intentional structural combination, and conjunction connected to the extensional one. So conditional fusion are connected to intentional combination, conjunctions connected to extensional combination. And there are other rules, disjunction, I'm giving you the fusion rules. Those are all fine and good. Okay, so now as a proof system, we want to know about the connection between the proof system and the models. What is the notion of validity that we're going to work with? And so now I'm going, I will now turn to the issue of reflexivity, because that comes in thinking about validity. Okay, so we have a sequent. What should it mean for this sequent to be valid? What are we looking for? Well, one idea is that whenever the structure on the left, gamma, is verified, we want the formula on the right to also be verified. All right, so that's the general idea we're going to work with. So filling it out just a little bit, we say whenever the structure is verified at a point, well, you might say whenever the structure is verified at a point, the conclusion is verified at that point too. So that is a fine and good notion of validity. The issue, or one thing to note about this, which was kind of surprising, is that the soundness of the rules there depends on having a reflexivity condition in place. In particular, the epsilon rules appeal to reflexivity if we use that definition. And so now, this is kind of curious, because if you're familiar with ternary relational models, frames, right, they all have a reflexivity condition, right? The ones that the presentation I gave, we required that the heredity ordering be a partial order or pre-order. In other versions, like reduced frames, they have a reflexivity condition. In the simplified semantics, Priest and Sylvan, they have a reflexivity condition as well. And you might wonder, how important is reflexivity? Can we get it to fail, right? You might want it to fail just to see what the logical upshots of that would be. And one other reason for sort of being tempted by non-reflexive relations is that there's a lot of them out there. There's a lot of things that are very close to being compositional, but for being, there's a lot of things relations that are compositional, but don't quite satisfy reflexivity. And so it would be nice to have a way to sort of bring those into the fold, so we have more models to try out our logical notions on, more areas to build intuitions about. So here's an example of a non-reflexive frame. So we take a set of points with the real numbers, and the relation here is going to be such that x relates to y, just in case y is strictly greater than the sum of the real numbers in x. So that is not reflexive because we are using strictly greater, but it is a pleasantly familiar relation. And the real line is a rich and interesting structure. And so that seems like something we'd want to have. If we could use it in modeling our logic, it'd be nice to have it in there. And so that turns out, jumping ahead slightly, that turns out to be a multiset, a good old compositional multiset relation. It's not reflexive. And so that gives us a frame for RW. Okay, so here's how we can incorporate non-reflexive frames. We can just drop that condition, and in doing so, actually generalize on the Routley-Meyer ternary relational frames, do something in this framework that can't be done in that framework. Okay, so what we'll do is tweak the original idea slightly, and I think in the spirit of the enterprise. So whenever the structure on the left of the sequence is verified at a point, the formula on the right is verified at a related point. And notice that if we have a reflexivity condition around, there's always a related point. So if we have reflexivity around, this idea, this tweaked idea collapses to the previous idea. And there's always a related point because with reflexivity, that's just what it says. There's always, there's always a related point, and in fact, it's the one you're at. Okay, but to get that to work, we need a few definitions. Give you a nice sense of how validity is working here. So first off, the extension of a formula, we'll define it like this. The extension of a formula is the set of points where the formula is true or is verified. And then for structures, we're going to work with a slightly different notion called the shadow of a structure. And basically, it's the stuff that is appropriately related to points via the R relation. So the shadow of epsilon is the set of points that the empty multiset relates to. The shadow of a formula is the set of things that are one step down from, are related to stuff in the extension. The shadow of an extensional combination is where the shadows of the two combined structures overlap. And the shadow of intentional combination, of an intentionally combined structure, is what you get by, putting this roughly, intentionally combining points from the shadows of the contained structures, or the combined structures. Okay, so here are three little facts about this notion of shadows and extensions. So first off, the shadow of a formula is always contained in the extension. And if the frame is reflexive, then the shadow is identical to the extension. So the distinction that we're making here really only comes into force when we're dealing with non-reflexive frames. And then, as you might have hoped from the description I gave of extensional combination, the shadow of an extensionally combined structure is the intersection of the two shadows. It really is just where they overlap. Okay, so now that we have the notion of shadow and extension, we can just define validity and say that a sequent holds in a model just in case the shadow of the premise structure is contained in the extension of the conclusion formula. Right, and a sequence valid in the class of frames if it holds in each model in each frame. Well, and so that's the notion of validity that we were working with, just a slight generalization of the sort of straightforward. The left-hand side is verified at a point, and the right-hand side is too. And the upshot of this is that the sequence system for RW plus is sound for this notion of validity. So every derivable sequent in the proof system is valid. And then if we wanted to get frames, multiset frames for R, so the proof system for R plus is sound, we just add this contraction condition, this contraction-y condition, which is the appropriate one for non-reflexive frames. There's a slightly simpler one you can use for reflexive frames, but this works out even for non-reflective frames. So the proof that's, the proof system is sound goes by induction on the length of a derivation, or like you would expect. And rather than walk you through the details of that, I will just highlight some features of the overall framework that come up in that proof. They're sort of interesting, I think they're interesting observations to sort of give you a feel for how the various bits and pieces are coming together. So first off, the identity axiom is valid even in non-reflective frames, right? We're working with a kind of reservation notion of validity, so we get identity valid. And so just as a reminder, we had these two conditions, transitivity and evaluation. They're part of being a compositional multiset relation. So on inspection, you might think, okay, transitivity, that just looks like cut. The soundness of cut just has to depend on that. That turns out doesn't appear to be true. Went through the proof quite a bit the last couple of days. Transitivity appears not to be used in the soundness of cut. Transitivity is used along with evaluation to show that some of the structural rules hold. In particular, the rule IB for the reassociation and the epsilon rules. There you use evaluation and transitivity to show that they are sound. And just to give you a sense of how that's working, the argument that IB is sound gives you a, if you work it out, it gives you several points. They're related. You stick them together, you stick those collections together using transitivity, and then you use evaluation to pop them off into different groupings. And then that tells you what you need to get soundness. Then if non-reflexive frames are under consideration, the soundness for the right, the conditional right rule uses evaluation. If reflexive frames are under consideration, you can just use reflexivity in arguing for the soundness of this rule. But if we don't need reflexivity, you can just use an appeal to evaluation, which you would sort of expect because reflexivity is one condition that just you can't seem to get away from in the ternary relational frames. Here we can drop it and trade it for an instance of this general evaluation rule. So now, so I mentioned epsilon and sort of the role of the epsilon rules, how those connect to evaluation transitivity. I'll mention another sort of interesting tweak on the collection frames. So we've been considering multiset frames where the multisets are just any finite multisets. That includes empty multisets, the empty multiset. But the empty multiset, is very special. Right? It has a lot of distinctive features. Right? It has a lot of these features in virtue of the fact that any multiset is identical to itself union empty. And so if we're using evaluation and transitivity, that has a lot of effect on how points are related to other, or points appear in different collections or in different multisets. For example, if you have the empty multiset relating to something, and that appears in a multiset with another point relating to, say, Z, you can just delete the ones that are related to by empty, and you still have the relation between the rest of the multiset and Z. And evaluation means that you sort of have the converse, that points that are related to by the empty multiset can just pop up in collections, which is, it's fine. It just causes some problems for it can cause some problems for finding frames. Like there are some things that are, some relations that are very tempting but don't work out because if you're considering the empty multiset, because one of transitivity or evaluation gets broken because you can't find something suitable points to be related to by the empty multiset. And then you might just wonder, how important is the empty multiset generally, or the empty collection, if you're being really general? How important? What is the effect of that? Well, let's explore that idea for a sec. So we can define a compositional multiset relation on non-empty finite multisets. Right? We just the earlier definition just said, okay, yeah, let's consider all finite multisets. But we can just focus on, we can zoom in on the non-empty ones, for example. And I think you could possibly zoom in on other subsets, but let's zoom in on the non-empty ones and call them inhabited multiset frames. You could have other inhabited collection frames too. So it turns out the logical upshot of these inhabited multiset frames is that the rules apart from epsilon and little t are sound for compositional inhabited multiset frames, reflexive or not. So the empty multiset, or empty collection, is really doing the job of the normal points in the ternary relational frame. We can drop that without, we can drop that here without any issue if we're okay with dropping epsilon and little t from our language. And this has sort of an interesting upshot, logical upshot. And there's a subtlety here that I want to flag. So the proof system with little t is conservative over the system with epsilon rules, but without little t. So we take our proof system with epsilon and without little t, and if we add the little t rules, the result is a conservative extension, right? That is, I think, in a relative well-known result. It turns out that the proof system with epsilon is not conservative over the proof system without, which at least I found kind of surprising because like little t and epsilon are so closely linked. And it's like, oh yeah, of course, if you just drop one, if you just drop, you have conservative extension with by little t with if you have epsilon, so it seems like why not? My expectation was that you would have conservative extension of epsilon over the epsilon-free system, but that's not true. So here is an example in case you do not believe me for some reason. Okay, so here is a sequence that is not valid for inhabited multiset frames, but it is a theorem of RW, right? So this is a theorem of RW. And you can, if you think about how this proof would go, right? If you want to prove this, what you would do is prove, get an instance of modus ponens, right, with this as a conditional, and then you have a copy of P implies P over here, and then you prove that P implies P is logical truth with an epsilon on the left, and then you'd cut, or if you're using cut there, and then you get rid of epsilon. But without epsilon in the system, there aren't logical truths. And so there's not a way to just drop them out of a sequence like that. So the logic of inhabited multiset frames is going to be very similar to RW, but it's not RW's. It's going to differ. And so there's a sense in which you can't just drop logical truths, well, because there aren't logical truths. So if you're sort of into some of the ideas from weaker relevant logics, you might think of this as a way of removing any option of suppressing theorems, because there's no theorem, so you can't suppress them. You can't just drop them out. Their effects will stay around. Yeah. So the logic of inhabited multiset or inhabited collection frames differs from the logic of general multiset or collection frames in an important way. And the logic for inhabited multiset frames is, I think, less well studied than the logic for other systems that use epsilon. The proof system without epsilon is less well studied than the proof systems with epsilon and with little t. So I think there's some interesting work to be done there in better understanding what's going on with those systems and how exactly they relate to the non-conservative extensions with epsilon. Okay, so what about completeness as a bridge to the next topic? So RW plus is complete with respect to multiset frame validity. Now it works out. R plus is complete with respect to multiset frame validity with the additional condition the contraction condition I mentioned earlier. And you can get this via a canonical frame argument because you can show that every ternary relational frame, there's sort of a way of defining a multiset frame from that. And then the canonical frame for RW is one of those that you can define. And so you can get whatever counterexamples that you want. And so then you might have the thought that you can get, well, you can get finite sets from finite multisets by sort of ignoring multiplicity, contracting copies together. So a natural thought that I had was that R plus is complete with respect to compositional set frames in the same way that RW plus is complete to compositional multiset frames. Right? The difference is that little bit of contraction, right? But that is not really working out. The completeness of R plus with respect to compositional set frames is still open, and the sticking point is sort of weird. The sticking point is that the canonical frame argument that I just mentioned via translation is not going to work, right? That's because set frames sort of impose this condition on the standard translation. Ends up having this condition coming out of the set frames, which is forced by the fact that we have this set relation, this thing from set theory. And it looks like the canonical R frame does not obey that. There are R frames that do not obey this condition, and the canonical R frame appears not to obey it. And so that question is still open. Which brings me to functionality in a place where the question is not open. Okay, so for most of the rest of the talk, I'm going to focus on reflexive compositional set frames that obey this functionality condition. So every set is related to a point. And if a set is related to 2 points, those are actually the same point. So I'll just call these things functional set frames. So these are reflexive compositional set frames that obey this condition. And so why are we looking at these? Well, while reflexive compositional set frames may not line up with R, that question's open. Functional reflexive compositional set frames line up with Urquhart's semilattice frames. So they give you semilattice logic, which is, I think, kind of exciting. So now, what is semilattice logic? What are semilattice frames? I'm glad you asked. Okay, so Alistair Urquhart, in his dissertation, some subsequent publications, present semilattice frames and models for the relevant logic R, as well as many other relevant logics. And he presents semilattice frames and more general operational frames. And so semilattice frame is a triple P join 0. 0 is a distinguished element of P, and join here is a binary operation on P to obey some conditions. Here are the conditions. The result is that join is a semilattice join. And if you look at them, you can see, all right, 0 can disappear. Order of the operation, you can kind of ignore it. Association of the operation, you can kind of ignore that too. And because of idempotence, you can toss out extra copies or introduce them as you want. Okay, so to get a model out of those frames, you take evaluation, and here are the verification conditions. Conjunction, disjunction are as they have been, and the conditional looks like this. For all, so A implies B is verified at X, just in case for all Y. If Y verifies the antecedent, then X combined with Y verifies the consequent. So that, and for this portion, fusion and little t and bottom are falling out of the language. So formula is going to hold in a semilattice model just in case it holds at 0. It's verified at 0, and it's valid in case it holds in all semilattice models. Which brings us to semilattice logic. Right, so the logic, I'll call UR, is the set of valid formulas. And that properly extends R. And so in that sense, calling them semilattice frames for R is slightly misleading because it does go beyond R. Although the implication fragment and the implication conjunction fragment do match exactly R. So there's a sense in which those line up. But with disjunction on the scene, semilattice frames give you more than R. So an example of a validity witnessing the proper extension, which I believe is due to Meyer and Dunn, is this one. It's a fairly standard example from the area. Just let you look at that. If you're wondering what's going on, the intuitive explanation is that you're taking this implication and detaching it into that disjunction and getting that out. That is not okay in R, not allowed. So that is invalid in R, valid in semilattice frames. Okay, so a little bit of background, a little bit of on the development of semilattice frames. So Charlwood, in his dissertation and subsequent publication, 1981, proves completeness for an axiomatic version of R with an additional rule. I'm not going to put the rule here. You can go find it in Charlwood's paper, dissertation, or the Greg Restall survey article. It is a impressive rule that is a lot. But it gives you completeness. And so Charlwood proves completeness, giving all the details, fleshing out an idea from an abstract from Kip Fine that claimed completeness for an extension of R using two rules. And one of Charlwood's accomplishments was giving some really cool proof theory that had the upshot of showing that Fine's second rule is actually admissible in the proof system with just the one additional rule. Cool. Okay, so one other sort of development in the area of semilattice logic is this paper by Humberson, where he shows how to augment semilattice frames with an additional operation on points. And that additional operation is used to interpret disjunction. So we get a different disjunction verification condition. And those augmented frames give you a definition of validity which you can prove, you get completeness for R. So R is complete with respect to validity defined with this, for these augmented semilattice frames. So if your target is R, right, you have a way to do that. If you just have to use a slightly different disjunction verification condition, which is, I think, natural and delightful, and I recommend the paper to you. And then there has been a bit more work, especially in the area of the operational frames, dropping some of those conditions that I had up earlier. But I will not stop to go over those here. If you're curious, I have a paper that will hopefully be forthcoming on semilattice semantics that goes over a little bit of that. Okay, so so that's background on semilattice frames. Now we want to relate semilattice frames to functional set frames. And here's how we're going to do that. We're going to define this big operation, big join, like this. So big join of empty is 0. Big join of singleton is the member. Big join of a slightly larger set is going to be the join of the members in this arbitrary order. And of course, since you can reassociate and permute and add or remove copies, the order does not matter. Okay, so let's say you have a semilattice frame and you want a functional set frame. How are you going to do that? Well, here's how. Say x relates to y, just in case y is the big join of x. Cool. That's well defined and gives you a functional set frame. All right, now suppose you have a functional set frame and you're really after a semilattice frame. Well, how do you do that? All right, so we define 0 as the x related, the empty set relates to. And you defined yeah, okay, so there's a question, is this defined for only finite sets, finite semilattices. No, the sets are all finite. So for all the collection frames, we're working with finite collections. So the size of P is not going to matter. Yeah, any frame, we're only working with finite collections. Yeah. What happens if you have infinite collections? That is a wide open area that you know, could be fun to explore. Okay, so let's return to, so you have a functional set frame, you want a semilattice frame. All right, so 0 is going to be the unique thing that the empty set relates to. And then say X join Y is identical to Z, just in case XY relates to Z. The set XY relates to Z. Cool. Okay, so now you have these two things. You might wonder, well, okay, what happens if you like alternate these definitions, these constructions? Well, we can prove round trip theorems showing that the constructions bring us back to where we started. So if you start with a functional set frame and then use a construction to get a semilattice frame, and then do it again to get a set frame, where you end up with is actually where you started. They're the same frame. And then if you have a semilattice frame and use the definition to get a functional set frame, and do that again to get another semilattice frame, you get back to where you started, same frame. So alternating these constructions take you back to where you started. And so get a nice little round trip theorem, hence the title of the slide. Okay, so we have these constructions to give you the frames back. And now you might wonder, okay, we get agreement on frames. Do we get agreement on models? Do we get agreement on counterexamples? Yes. So given a source frame, we can construct a target frame, right? And then if we have a valuation on the source frame, so we have a model, that actually pretty immediately gives you a model on the target frame. And you get point-by-point agreement on all formulas. So a counterexample in one setting gives you a counterexample in the other setting. So that is good and exciting. The upshot of this is the logic of functional set frames is the logic of semilattice frames. So now, question. Is the logic of possibly non-functional set frames also semilattice logic? Right? It's not, have not proved that it's R, so maybe it could just properly extend it in that direction. Suspense. No. It is not. Not sure exactly what it is, but it's not that. I know of no better way to justify that to you than to just give you a counterexample. Here we have a non-functional compositional reflexive set relation on a set with 3 points, ABC. And here is a verification relation. It is hereditary. And here is an example of a validity of semilattice logic that is a counterexample there. So one of the things I've highlighted a couple of times in the course of the talk is that it is relatively easy to find frames for the stronger logics like R, RW. And that's kind of, that's a heuristic thing that just, it seems to be easier to find them and to verify that you have a frame for these logics. One of the nice things I found about set frames in particular is that they are sort of amenable to computational exploration because they are nicely finite. And so this frame I actually found by writing up a little program in Python to find frames that satisfy certain conditions. And it gave me this one and it worked out. So I think they're, Okay, so that is the meat of the talk. I'll just sum up with a couple of conclusions because that may have been a lot. So, so first thing that I have not really argued, I hope I presented some evidence for this, but collection frames provide a rich framework for investigating relevant logics. You can work with your favorite collection of stuff, kind of collection, and see what sort of logic results from that. And if there are any sort of natural connections to other areas of relevant logic or substructural logics. Okay, next major point, there's a natural definition of validity on collection frames that works with non-reflexive frames. So it does give us a proper generalization of ternary relational frames. Functional, okay, so that point, functional reflexive set frames yield exactly the same logic as Urquhart Semilattice frames. So while the logic of set frames is still a little bit up in the air in the sense we don't know exactly what it is, the logic of functional reflexive set frames, compositional set frames, does match Semilattice logic. And the logic of set frames is at least properly contained in that. And so now, if you are curious for a little bit more about how collection frames work and would like to see a little bit more, Greg has a talk on YouTube, Geometric Models for Relevant Logics. It looks at some application of this in the area of geometry, connecting to some of Alistair Urquhart's other work. And the general theory paper is on Greg's website there. So if you are interested in that stuff, I commend that to you for further exploration. All right, thank you very much.
Thank you. It's a good time for comments, questions, discussion. If you've got a question, stick it in